Section 20.3 Eigenvalues and Eigenfunctions for the total energy. Section 20.4 The hydrogen atom orbitals. I put these two sections together in the same video because we will look at the eigenvalues and eigenfunctions for the total energy of the electron in the hydrogen atom. And the hydrogen atom orbitals are described by these eigenfunctions. The atomic orbital energies are the eigenvalues. So let's look at the expression of the energy of the electron in the hydrogen atom. It is quantized. Over here, this n must be an integer. N is 1, 2, 3, 4. N is the principal quantum number. And pay attention to the negative sign. This is the mass of the electron, the charge of the electron. Epsilon 0 is the vacuum permittivity. H is the Planck constant. This expression is rather complicated, but it can be dramatically simplified in the atomic units. There are 4 fundamental atomic units: charge, mass, angular momentum, and Coulomb's constant. So the absolute value of the charge of an electron is defined to be 1 atomic unit of charge. The mass of the electron is 1 atomic unit of mass. H bar is 1 atomic unit of angular momentum and 1 over 4 pi epsilon. This whole thing is defined to be 1 atomic unit. So 1 atomic unit of energy can be derived based on the 4 fundamental atomic units. 1 atomic unit of energy is also called 1 Hartree or 1 E sub h, and over here this is the expression of 1 atomic unit of energy. And this whole thing is 4.36 times 10 to the power of negative 18 joule, or 2,625.5 kilojoule per mole. You can convert it to kcal per mole. You can convert it to electron volts. And also, you can convert this to the wave number here. But energy is H times C times the wave number. The reason you see these two quite different numbers is because over here, we're talking about 1 particle or 1 electron. Over here, we're talking about 1 mole such electrons. So these two numbers differ by the Avogadro constant right here. Now let's look at the atomic orbital energy levels of the electron in the hydrogen atom. So it's this. And again, we can convert this to atomic units. Over here, this is conversion. This is purely algebra. We're just trying to make sure this Me is 1 atomic unit. The charge of the electron is 1 atomic unit. And 4 pi epsilon is 1 atomic unit. H bar is 1 atomic unit. And then the result is negative 1 over 2n squared atomic unit of energy. So 1 atomic unit of energy is this. Again, this is just 1. Because again, M sub E is 1. This charge of the electron is 1. 4 pi epsilon is 1. And H bar is 1. So I want you to be able to memorize this equation. This is very simple. Negative 1 over 2n squared. That gives you the atomic orbital energy. So the energies of the 1s, 2s, 3s, 4s atomic orbitals in the hydrogen atom are simply negative 1 over 2, 1 over 8, 1 over 18, negative 1 over 32 atomic units, respectively. What about 2p, 3p, 4p? Well, it's just negative 1 over 8, negative 1 over 18, negative 1 over 32. 3D, 4D, they are here. I want to add this in the hydrogen atom. Alright, so this is true for the hydrogen atom. Well, if you look at some other atoms with more than 1 electron, then you will see the 2p atomic orbital energy is higher than the 2s atomic orbital energy. But right here, 2s and 2p have the same energy, negative 1/8. All right, 3s, 3p, 3d, they have the same energy. Well, negative 1/18. This is true for the hydrogen atom or for hydrogen-like one-electron system. Now let's look at some numerical examples. We can calculate the wave number and wavelength of the photon emitted in a 3D to 2p electronic transition of a hydrogen atom. So really we just need to calculate the energy difference between these two orbitals right here. This is in atomic unit, and then one atomic unit is this. All right, and then we can easily calculate the wave number of the photon. It's this. All right, and lambda is 1 over the wave number. It's 656 nanometers. This is a red light. We can also define the atomic unit of length. It's this. In the SI units, it's 0.529 times 10 to the power of negative 10 meters. And 1 angstrom is 10 to the power of negative 10 meters. All right, now let's look at the Schrodinger equation for the hydrogen atom in the SI units. What's this? Over here, you are looking at the kinetic energy operator. Looks very complicated. And this is the potential energy operator. So over here, this is attraction between the electron and the nucleus. Now we can simplify this Schrodinger equation. Again, the mass of the electron is 1, the charge is 1, h bar is 1, 4 pi epsilon is 1. So now we have a simplified equation in the atomic units. Now how do we solve this? Well, we are looking at 3 variables, r, theta, and phi. So the first step is always separation of variables. So we're assuming this wave function of the electron is the product of 3 functions. A function of r, a function of theta, a function of phi. But very often we combine these two. So these two are both angular functions. We combine these two, we say, well, the product of theta and phi is a function y. Y is the angular function for the electron. And now let's look at some numbers here. N, L are integers. N is the principal quantum number, L is the angular momentum quantum number, M sub L is the magnetic quantum number. So L give you the angular momentum of the electron, and M sub L give you the Z component of the angular momentum. All right, so first let's look at this radial functions, the functions of r, the radius. Well, if you look at the 1s orbital, it looks very complicated. It's 2 times this guy times e to the power of negative r over a naught. But remember, a naught is 1 atomic unit of length. So, if we are using the atomic units, this can be expressed as 2 times e to the power of negative r. That's it. Again, 2 times e to the power of negative r, if we are using atomic units. Right here, you're looking at the SI units. So this A naught is 0.529 times 10 to the power of negative 10 meters. Now over here, this is the 2s orbital. You are looking at the radial function of the 2s orbital. This is the radial function of the 2p orbital. If you compare this to, you'll see over here, there's a spherical nodal surface, right? R equals 2a naught. So when r is equal to 2 times 0.529 angstroms, well, this wave function, this radial function is 0. That's why you see a spherical nodal surface in the 2s orbital. You don't see that in the 2p orbital. All right. So for the 2p orbital, you need to multiply this radial function with its angular function. And then you will see if you have 2px, the planar nodal surface is at x equals 0. 2py, y equals 0. 2pz, when z is 0, you have nodal surface. Now you have 3s, 3p, 3d. Those are, again, the radial functions. So over here, if you solve this equation, set this to be 0, you get two solutions, two roots. These two roots correspond to the two spherical nodal surfaces in the 3s orbital. And over here, you can immediately tell, well, when r is equal to 6 times a naught, you have a nodal surface, a spherical nodal surface, when r is equal to 6 times a naught. From this equation for 3D, you can see there's 0 spherical nodal surface. However, when you multiply this with the angular function of the 3D orbital, you'll see there are two planar nodal surfaces in each of the 5 3D orbitals. Okay, again, this is a naught atomic unit of length, and a naught is 0.529 angstroms, or 0.529 times 10 to the power of negative 10 meters. And this is 1 atomic unit. So over here, I'm using atomic unit here for this radial functions. And you'll see these expressions are much simpler. You're not seeing those a naught here or there. So really, I just replaced every r over a naught with r, because a over r naught is r over 1 atomic unit of length, so that's just r in atomic units. All right. You might be confused by those coefficients, 2, 1 over square root of 8. Those are just normalization factors. These normalization factors are here to ensure the integral of the squared modulus of the radial function with respect to the volume element, or the radial part of the volume element is 1. So this is just to ensure the probability of finding the electrons in the entire space is exactly 1. We can verify that these radial functions are normalized. For example, if you use Wolfram alpha, you can click this and type integrate 4 times e to the power of negative 2r times r squared from 0 to infinity. The result is 1. So why this? Well, we'll just have to integrate the squared modulus of the wave function. So you need to integrate the squared modulus of this function. This function is a real function. So the squared modulus of a real function is simply this function squared. So you have 4 times e to the power of negative 2r as the squared of r1, 0. All right, so this part. So what about this r to the power of 2? This is because the volume element in the polar spherical coordinates is r squared times sine theta times dr times d theta times d phi over here. So that's why you have r squared here. All right, so that's where r squared comes from. And then you integrate this whole thing from 0 to infinity. The result is 1. You can also check this. What is this? 4 over 81 to the power of 2 divided by 30. It looks really complicated. But really, it's just this. I'm trying to show you this radial wave function is normalized. Oh, I'm sorry. It's R32R. So this one. So I'm trying to show you the integral of the squared modulus of this function times r squared dr is 1. All right, you can click this web link to see the derivation on Wolfram alpha. Do not try to memorize the normalization factors. They are not very useful other than normalizing the wave function. So with or without those normalization factors, you will get the same shape of the atomic orbital. You'll get the same energy, same atomic orbital energy for each orbital. So it doesn't really matter that much. However, I want you to again pay attention to the nodal surface, because when you look at this wave function, this is the radial part of the 2s orbital. So again, this n equals 2, L equals 0. When L is 0, this is 2s orbital. I want you to be able to find where the nodal surface is. When r is equal to 2, this function is 0. So we have a spherical nodal surface when the radius is 2. Similarly, if you're looking at this 3s orbital, you should be able to solve this equation to determine where these two nodal surfaces are. So when r is 1.5 times 3 plus minus the square root of 3, you have two nodal surfaces. So these two numbers are actually 1.9 and 7.1 atomic unit of length. Again, one atomic unit of length is 0.529 angstroms. Now let's look at the angular functions. So you can see the 1s angular function is a constant. It does not really depend on theta and phi. But if you look at pz functions, it does depend on theta. Px and py, it does depend on theta and phi. And what about z squared? Well, dz squared, well, it depends on theta. The xz, the yz, well, it depends on theta and phi. Same here, theta and phi. So these functions, sometimes they are functions of both theta and phi. Sometimes they are functions of theta only. And sometimes they are a constant. When you see a constant, it's got to be an s orbital. S orbitals do not depend on theta or phi. So again, there are two quantum numbers over here. This means L equals 2. The subscript L equals 2. Plus minus 2 are the values of m sub L. So this is when m sub L is equal to plus 2 or minus 2. Again, L equals 2. M sub L is plus 1 or minus 1. L equals 2. M sub L, the z component, is 0. L is 1, M sub L is plus minus 1. L is 1, M sub L is 0. L is 0, M sub L can only be 0. Alright, so again, those are just the angular functions of the electron in the hydrogen atom. We can look at the shape of those angular functions. You probably can tell this is just px, pz, py, dz squared, dxz, dx squared minus y squared, dyz, and dxy. I want to emphasize the difference between dxy and dx squared minus y squared. This and this are both on the xy plane, but they have different nodal surfaces. So over here you can see when x squared minus y squared is 0, you have two nodal surfaces. That means when y equals plus minus x, you have two nodal surfaces. Right here, you also have two nodal surfaces at x equals 0 and y equals 0. So you have different positions of the two planar nodal surfaces. So when I draw this orbital and this orbital, I usually draw the nodal surfaces first, and then I draw the four lobes. Alright, so if you put the radial function and the spherical function together, you get the product. The product is the entire eigenfunction of the Hamiltonian operator of the hydrogen atom. 1s orbital. You have the radial function, you have the angular function, you do a multiplication, put them together, and then you get this wave function. Over here, I'm using n for normalization function, or normalization factor, because it gets really tedious. In this case, this uppercase n, this normalization function, is 2 times 1 over a naught to the power of 3 halves times 1 over the square root of 4 pi. This is really complicated. And over here, also, you have a normalization function. I'm just call that n. Alright, this is for the 2s orbital. 2pz orbital, same here. If you're looking at the product of the radial function and the angular function, you'll see a fairly complicated normalization function, which is 1 over the square root of 24 times 1 over a naught to the power of 3 halves times the square root of 3 over 4 pi. Okay, I have never been able to memorize this normalization functions because it's not important at all. Alright, but I want you to look at this r here. This is important. Times cosine theta, that's important. R times cosine theta, that's important. And then times e to the power of negative r over 2a naught. Alright, so these two parts are very important. And r times cosine theta is simply z. So it's just z times an exponential function. Alright, and if you look at 2s and 2pz, they have the same exponential function, e to the power of negative r over 2a naught, e to the power of negative r over 2a naught. All right, so if you look at 2px, 2py, they also have this exponential function. What about 1s? 1s has a exponential function, but for 1s orbital, it's e to the power of negative r over 1a naught. What about 3s, 3p, 3d? E to the power of negative r over 3a naught. All right, so over here, you'll see 2p plus minus 1. It's not 2px or 2py. 2p plus minus 1 are the linear combinations of 2px and 2py. So the expressions here, again, this n is the normalization factor. So if you put this constant and this constant together, you get this n. And now you can see these two functions. When m sub l is plus 1 or negative 1, you get a complex wave function. So this part is a complex function, e to the power of plus minus I phi. However, if you do a linear combination of e to the power of plus minus I phi, you can get cosine phi. You can get sine phi. And cosine phi and sine phi will be multiplied by this r times sine theta. And r times sine theta times cosine phi is simply x. R times sine theta times sine phi is simply y. So you are looking at linear combinations of px and py. Now let's use atomic units. If you look at the atomic units, the wave functions become much simpler. So this is the unnormalized wave function of 1s, 2s, 2pz, and over here, this is a linear combination of 2px and 2py. So I'm going to just do some combination here. I want to show you how can we go from 2p plus minus 1 to 2px. We just sum it up, and then we get 2 times x times e to the power of negative r over 2. And this part is the unnormalized wave function of 2px. All right, so a little bit mathematics here, but really you need to know this is cosine phi plus I times sine phi. This is cosine phi minus I times sine phi. So if you put these two together, you get 2 times cosine phi. Well, similarly, if you take the difference between 2p plus 1 and 2p minus 1, you'll get this 2py wave function multiplied by a constant. All right, and y times e to the power of negative r over 2, this part is the unnormalized wave function of the 2py orbital. So really, in general chemistry, you learned there are 3 2p orbitals, px, py, pz. However, px and py are not direct solutions to the Schrodinger equation of the hydrogen atom. All right, it's actually 2p plus 1, 2p minus 1. These two are complex functions. Okay, these two are complex functions. But if you do a linear combination, you sum it up, you take the difference, you will be able to get 2px and 2py. Just a reminder, x is r times sine theta cosine phi, y is r times sine theta times sine phi, and z equals r times cosine theta. So again, these two are the unnormalized wave functions of 2px and 2py. They are two linear combinations of 2p plus minus 1. Plus 1, minus 1 are the values of m sub l. Okay. When the principal quantum number n equals 3, we have 3s, 3p, and 3d orbitals. So this is the unnormalized wave function for the 3s orbital. Those are unnormalized wave function for the 3p atomic orbitals. And you can immediately tell where the nodal surfaces are. When r equals 6, you have a spherical nodal surface. When x is 0, you have a planar nodal surface. When r equals 6, when y equals 0, when I equals 6, when z equals 0. What about 3dz squared? dz squared has also 2 nodal surfaces. This is when 3z squared is equal to r squared. So that means when z is equal to r over the square root of 3, or when z is equal to negative r over the square root of 3, we have 2 nodal surfaces. And remember, z is r times cosine theta. So really, when cosine theta is equal to positive 1 over the square root of 3 or negative 1 over the square root of 3, we have two nodal surfaces. And then you have two different values for theta, and you will be able to picture the shape of the two nodal surfaces. There are two cones. Surrounding the z-axis. Now, these three are really easy. You can see the nodal surfaces are here when x equals 0 and y equals 0. Over here, when y is 0, z is 0. Over here, when x is 0 or y is 0. And then you have two nodal surfaces in each of these three wave functions. What about 3D x squared minus y squared? Well, we set this part to be 0, and then when y equals x, you have a nodal surface. When y equals negative x, you have another nodal surface. All right. Over here, this is just a simple derivation to show you where the nodal surfaces are in this 3D x squared minus y squared atomic orbital. So again, this is a solution. When x equals plus minus y, we have two nodal planes. I want to show you the shape of the 1s, 2s, 3s orbitals. There's a 0 node here, 1 node here, and 2 nodes here. Those are the functions. What about the shape of the 2pz orbital over here? It looks a little weird, but this is the reality. So if you're trying to measure the position of a 2pz electron, if you do 1 million measurements, very likely you'll get 1 million different positions. However, if you put this 1 million positions together on the same graph, you'll see something like this. This is your 2pz orbital. There's a nodal plane when z equals 0, all right? But then the electron can appear anywhere else. As long as z is not 0, it's possible to observe the electron there. So even here, right? Even here, and here, and here. All right, but it's more likely to observe the 2pz electron in this region and in this region. Okay. Well, now let's do some mathematics. Let's prove this wave function is indeed an eigenfunction of the Hamiltonian operator of the electron in the hydrogen atom. All right. So we'll have to plug in that wave function here. This psi is equal to this guy. It's really complicated. But A naught is just a constant. Again, A naught is just one atomic unit of length. A naught is 0.529 angstroms. So you just plug in the wave function and just derive this. You will be able to get the result in the expression of the initial wave function multiplied by a constant. That constant is the energy of this orbital. So let's make it a little easier. Let's use the atomic units. So this is the Hamiltonian in atomic units. And this 1s wave function is simply e to the power of negative r times the normalization factor. All right. So why don't we use the atomic units to do the derivation? So I am about to apply this Hamiltonian to this wave function, and hopefully we will see this wave function appear as part of the result. The result should be this wave function multiplied by a constant. And that constant is the eigenvalue. And that eigenvalue has a physical meaning. That's the energy of this wave function. All right? So we're going to do that. So we apply the kinetic energy operator to the 1s function. This is potential energy operator to the 1s function. And then we just derive. There's not much to talk about, except this. This 1s wave function is a function of r, and r only. So when you apply delta over delta theta to the 1s function, you get 0. When you apply the second derivative of phi to this 1s wave function is 0. So that's why you can just get rid of these two terms, because 1s orbital does not depend on theta, it does not depend on phi. So this is a trick to simplify the derivation. So I want you just to look at the derivation and be able to do this yourself. In the end, you will get this as the result. Over here, this is the 1s wave function, and n is the normalization factor. In this case, I think n is 1 over the square root of pi, but who cares? You'll see. I mean, it's just you just need to keep n everywhere. N here, n here, n here, n here, n here, n here. So in the end, you have this n. So with or without this normalization factor, you will get the same result. You will get the same eigenvalue, which is negative 1/2. Okay, negative 1/2. And this is the eigenvalue. This is also the energy of the 1s electron. The 1s electron has negative 1/2 atomic unit of energy. We'll do something more complicated. Let's verify this 2pz wave function is also a legitimate solution to the Schrodinger equation for the hydrogen atom. All right, so we have a much more complicated wave function here. All right, n is the normalization factor, r times cosine theta, that's z. And over here, this exponential function is e to the power of negative r over 2. So actually, the exponential part is always e to the power of negative r over n. N is the principal quantum number of the electron in the hydrogen atom. Mathematics. Again, this is just the kinetic energy operator. This is the potential energy operator, both in atomic units. And this is just mathematics. 2pz does not depend on phi, so we don't have to worry about this term, but still, the derivation is more complicated. All right? But if you do everything carefully, in the end, you should be able to get this result. If you want to, I want to show you this. If you want to, you can freeze the video here and just try to derive this yourself. All right, and then I'm gonna show you this part again. You can pause the video and you derive these steps. And finally over here, hopefully you will also get this result. Negative 1/8 times the wave function of 2pz. So negative 1 over 8 is the eigenvalue of this 2pz wave function. That means 2pz has this energy, negative 1/8 atomic unit of energy.